This question was asked in the GATE Physics paper 2021. This is a MCQ type 1 mark question and the question was asked from the topic solid state physics. The question is, as shown in the figure, X-ray diffraction pattern is obtained from a diatomic chain of atoms P and Q. The diffraction condition is given by A cos theta equals to n lambda, where n is the order of the diffraction peak. Here, A is the lattice constant and lambda is the wavelength of the X-rays. Assume that atomic form factors and resolution of the instrument do not depend on theta. Then, the intensity of the diffraction peaks is option A, lower for even values of n when compared to odd values of n. Option B, lower for odd values of n when compared to even values of n. Option C, 0 for odd values of n. And the last option, option D, 0 for even values of n. So we have to choose the correct option. In order to solve this question, what we have to find is that the resultant scattered X-ray intensity on a particular plane as a function of the order of the diffraction peak. Let us see the solution. According to the question, we have to deal with this diatomic chain of atoms P and Q, where the distance between consecutive atoms P and Q is A by 2 and the lattice constant is A. If we look into this one-dimensional crystal structure carefully, then we can find that unit cell of this crystal structure will be this. This unit cell consists of two bases, that is P and Q. From now onwards, we will use only this unit cell for our future calculations. The diffraction condition is given by A cos theta equals to n lambda. Now we will multiply 2 pi by lambda on the both sides. So we will get 2 pi by lambda into A cos theta equals to 2 pi n. Now 2 pi by lambda is k naught, which is basically magnitude of incident X-ray wave vector. Our diffraction condition then becomes k naught A cos theta equals to 2 pi n. One more thing we have to consider, that is atomic form factor of the atoms P and Q. Now the atomic form factor or the atomic scattering factor is defined as amplitude of scattered X-ray radiation from an atom divided by amplitude of scattered X-ray radiation from an electron in that atom. So Fp is the atomic form factor of the atom P and Fq is the atomic form factor of the atom Q. Now consider this schematic diagram. So the X-ray radiation will incident on the atoms P and Q. The electric field of the incident radiation is given by E naught vector e to the power I k naught x, which is basically a plane wave equation. And then the X-ray will get scattered from P and Q. Here we will be considering only the scattering at an angle theta. Also we will assume a plane AB which is perpendicular to the scattered X-ray radiation from P and Q. After scattering from P atom, the X-ray beam will gain some extra phase due to the path length PC on the plane AB. Now the PCQ triangle is a right angle triangle. So PC is given by PQ times cos theta. Hence PC will be A cos theta by 2. So the extra phase gained by the scattered X-ray radiation from P atom will be k naught A cos theta by 2. Q atom is placed on the plane AB. So the scattered radiation will not effectively gain any phase on the plane AB. So resultant electric field of scattered X-ray radiation on the plane AB is given by Fp E naught vector e to the power I k naught x plus k naught A cos theta by 2 plus Fq E naught vector e to the power I k naught x. So first term is due to the X-ray scattering from P atom and second term is due to the X-ray scattering from Q atom. If we take E naught vector e to the power I k naught x as common, then we will get this. Now we will apply the diffraction condition, that is k naught A cos theta equals to 2 pi n. Then we will get ER vector equals to E naught vector e to the power I k naught x multiplied by Fp e to the power I n pi plus Fq. Therefore, the resultant intensity on the plane AB is given by IR proportional to electric field multiplied with its complex conjugate. So, IR proportional to E naught square into Fp e to the power minus n pi plus Fq multiplied with Fp e to the power in pi plus Fq. If we just multiply these two terms, then we will get E naught square multiplied with Fp square plus Fq e to the power in pi plus e to the power minus in pi plus Fq square. Now from the complex number theory, we know e to the power I theta plus e to the power minus I theta equals to 2 cos theta. Applying that formula, we will get the resultant intensity is proportional to E naught square multiplied with Fp square plus Fq square plus 2 Fp cos n pi. Hence, we found the resultant intensity as a function of the order of diffraction. Here, two possibilities will come. One is for odd values of n and other one is for even values of n. For the first case, n equals to odd, this cos n pi equals to minus 1. Effectively, we will get IR proportional to E naught square multiplied with Fp square plus Fq square minus 2 Fp. So for n is equal to odd, it will be E naught square multiplied with Fp minus Fq whole square. Similarly, for n is equal to even value, cos n pi will be plus 1. Hence, we will get the resultant intensity for n is equal to even proportional to E naught square multiplied with Fp plus Fq whole square. Clearly, it has been seen that this resultant intensity for n is equal to odd less than the resultant intensity for n is equal to even. So, among the four options, the option B is correct answer. So, the option B is lower for odd values of n when compared to the even values of n. This is the correct answer for this question.